Hello and welcome to this 3D example video. Let's start right away with a clean workspace, so copy it. ABMT 14 examples X is like in all the other videos from this example series. ABMT 14 ABMT X is clean. So robot arm is the example. Let's start. We start with compiling. Look what we have here. Here's a 3D scene, some parameters. Now let's open the model. So you have a composition of a scene, rod joint, rod joint, rod joint, parameters, a base, grid, an axis. It's already started, so let's see what we see here in the scene. So we can adjust the length of the rods, we can adjust the angles of the joints. So yeah, this is it. And now look into details how this is all done. Okay, so let's start with the scene. So what we have here, we have a scene composition, and we see that we add all kind of scenes together. So let's show you something here. I add another 3D scene here, and let's look at rod scene. So we add rod scene here. So do it like this. So this is only the scene that contains this rod, and when I change the length of rod 3, we see that this is changed. So now let's look into how this is all made. I stop this here, and we look at the home page. So look at the documentation for 3D. And we see here there's an operator multiply, which multiplies a pose with a scene, and it's creating a deep copy. So now what is a scene? We see that here. A scene has cubes, models, splines, points, and lines, and these are all arrays or vectors of shared object. We can copy a scene, this makes a deep copy, and we can add other scenes to this scene. So, and here are the details of these implementations we can add. So a cube has a position, a color, a size. A model has a pose and a path to the model. A point has a position, a color, and a size. Splines have a position, a scale, a path, or an image. And a line has a point 1, point 2, and a color. And methods ray and length. So you can calculate the length or get a ray out of it. Look shortly into math. We have vectors, we have matrices, and we have rays and a pose. This is the one we have. This is basically a Davenport-Hallberg parameters, a matrix with 4 rows and 4 columns, and it has nothing special more. It has this special attribute, so you can get the position out of it, and yeah, that's basically it. So yeah, I think you have to look a bit deeper into this yourself, but let's play a bit around with the model. So what we are doing here, let's delete this, this is not needed anymore. Let's start this again. So what we are doing is we are we have these rods, and these rods, for example, they have a cube that have a size, that the size is taken from these parameters, and the position, it moves this cube, moves it to set to the size and a half, and the next position will be at the end of the cube. So the idea is, let's explain this once again. We get into a position, so the cube begins here. It only has a size to grows into the set position, and here pos next will be at the end of the cube. So this is the beginning of the cube, this is the end, and at this end we add a joint. This rotates. Look into this a bit. So this creates a rotate pose and calculates the position out of this rotation. So you get a new position, then you add another rod, it grows in Z, and then you add another joint, and so on. So, and then you add all the scenes, all these elements, you add together to get this big scene. So how does this work with this one interesting thing you may need to know, how you move objects around in this world. So let's show you this. This done with expressions and this operator. So I show you this not here in this example, but we add something different here. We add a car. So let's do this. Let's take a model. So we have created a model scene. Scale is okay. In opt, there's a car. GLB, we only support GLB as format. So now let's add this, start all over again, and see what we have. So here we have a beautiful car that's rotated not like we want it. So let's rotate this. Here we have axis, it's RGB, R is X, G is green is Y, and blue is Z. We don't see Z. Do we have another? Let's rotate. No, this is, yeah. So we don't see Z. So it's Z is the height of the car here. So now let's rotate this. We want to rotate it at the x-axis, x-axis in a negative direction by pi half. So let's do this. Rotate. And we want to have the vector is x. The angle is pi. Pi is 3. Pi is 3. No. So it's good enough. And now let's take an expression and we pose my scene. So let's do this and I'll explain you why this is working. This is what we want. Ah yeah, I said minus pi, right? Minus pi half. So here we have it. And this is all, so no. And this is done, you read this from right to left, not from left to right. So I show you what I mean by, let's move this car also a bit around. So let's take another P2, P1. So first rotate and then move to position, move. So now let's make this into the, done something wrong here. So now let's move this 5 meters. So 5. Yeah. So x5. Does this work? Ah, okay. So now it's moved 5 into the x direction. So, and you read this. This is done because of mathematics and matrix multiplication law. So first it's rotated, then it's moved. So read from right to left to understand this composition of the motion. Yeah. So let's do something else. Let's add another object. Let's add a spline. So we can also add images. Let's take a webcam, and we also add a plane. The scaling, that's okay. So 1 pixel is 100th of a meter, or 1 in this 3D scene. So let's look how that works. There it is. Here we go. Thank you for watching. Bye bye.